Okay, so we're going to go over 13.1, the nature of gases. So the first thing you definitely need to know for your quiz is the kinetic molecular theory. And sometimes your teachers may actually abbreviate it KMT. Now, these are some characteristics of gases that we assume are true, and it's important that we assume these characteristics are true so that we can do gas law equations, which you guys will get into in chapter 14. So it's very important that you know these three assumptions or three characteristics of gases. The first one that we'll talk about is that gases are small, hard spheres. So they're small, hard spheres, almost like little bouncy balls. And we also assume that they have insignificant or very small volume. Now, the reason why that's important is when we get into the gas laws in chapter 14, we will be doing different calculations with volumes and temperatures and pressures. So it's very important for us to assume that gases take on the volume of their container that they're in. So we always assume that one single gas particle is so small that the volume is insignificant. The second thing that we assume is true for the kinetic molecular theory is that gases move in a constant, rapid, random motion. So what that means is gas particles we assume are constantly always moving. So if you imagine those little bouncy balls, like a little plastic bouncy ball, if you were to bounce it into a small room, that ball would just keep bouncing off all the walls. That's what we assume how gas particles behave. So they're constantly moving, they're rapidly moving, meaning moving very quickly, and they move in random ways. So there's no kind of rhyme or reason as to how they move, they just keep bouncing. And then the third thing that we assume is true is that gases have elastic collisions. So if you think of like a rubber band is elastic, meaning if we were to stretch it and let it goes back to being pretty close to its normal shape or its previous shape. So for gases, we assume that when they hit each other and they hit the walls or hit other objects, that they just bounce right back off. So they don't hit and stick. And so one other thing that's really important as to why we assume gases keep bouncing when they hit other things is that we assume that they have no attractions. So they have no attractions to other molecules, they have no attractions to the walls of a container or the walls in a room. So we assume that when they hit each other, they're not hitting and sticking, they're hitting and bouncing right back off. So these are three important things you need to know for the kinetic molecular theory. So there was a question, I believe, on your worksheet that says something about why would a tire explode or be more likely to explode in the summertime than in the wintertime. But the idea is, in the summertime, the pavement is very hot, the outside temperature is also very hot, and so those gas particles actually move a lot faster than they normally would, and they hit on the inside of the tire. And tires do expand a little bit, but not a lot, not like a balloon. So the more that those gas particles hit the inside of the tire, the more pressure they create, and the tire will explode. So now we'll actually get into talking about pressure. So the next thing you definitely will need to know for your quiz is what pressure is and why is it important in relationship to gases. So I'm sure you've heard of the word pressure before outside of a chemistry classroom, but pressure in general, we're going to keep track of how pressure changes, and in chapter 14 you'll be able to actually calculate the exact pressure of different things and how the temperature may affect pressure and how volume may affect pressure. So for right now, let's just start with the definition of pressure. So by definition, and your teacher will probably quiz you this, want you to know this definition. By definition, pressure is the force applied on a certain area. So the force applied on a certain area. Sometimes you might actually see this equation, P meaning pressure equals force over area. So what that would mean is the larger the area, imagine us like pushing down on something, whether it's a balloon or a ball, the more force we can push down on it If it's a smaller area, we can create more pressure. If we're pushing down on a larger area, we're not creating as much pressure. But this is one equation. Just be familiar with the idea that pressure is force applied on a certain area. Now, when we're talking about gas pressure, we're looking at how the particles are hitting each other and how they're hitting the environment around them. So how a gas particle may be hitting into another gas particle and how it may be hitting into, let's say, a tree or a house or other things. So the more the collisions that a gas has, the more pressure or the more force that it can have. So one thing of doing that is I'll say the higher the collisions, so the more collisions that a gas has, the higher the pressure the gas creates. And we'll talk about collisions in a second. So there are different ways that we can have gases or encourage gases to have more collisions, and there's ways that we can actually have gases have less collisions. But one thing that we assumed was true is gases are always moving. We can slow them down a little bit, but gases never stop moving. So keep that in mind. Gases are always moving. So one thing that we actually can do, if we wanted to, let's say, decrease the collisions or slow the gases down a little bit, is we can decrease the temperature. So if you decrease the temperature, the collisions actually will decrease. And the reason why that is, temperature gives energy to gases. So the more temperature or the more heat that's around a gas, the more energy it gets, and the faster the gas will move and the more collisions it will have. So if we decrease the temperature, kind of slowing everything down, kind of like in the wintertime, it kind of slows everyone down, it slows the gas particles down as well. So there was another question, I believe, in your packet that said, assume a camper has an air mattress. And let's say the air mattress in the morning when he wakes up seems to be a little bit deflated than it was the afternoon before when he blew it up. And so we'll assume that there's no leaks in the mattress. And the idea with that is if it's a cool, let's say, fall morning or a cool spring morning, the temperature is lower than it was the afternoon before. And so those gas particles aren't moving as quickly inside of that mattress. And so they're not hitting or creating pressure or force inside the mattress. So the mattress will look like it's deflated. But if we were to let that mattress heat up, so let's say we let it stay out in the sun for a couple hours, then the mattress should go back to being the same kind of height and inflation that it was before, because those gas particles will heat up, they'll get more energy, they'll have more collisions, they'll create more pressure. So for gases, if you think about temperatures, temperature is going to be affecting your pressure. So if it's high temperature, you have more collisions, more pressure. Lower temperature, slow those gas molecules down. They're not hitting each other as often. It's going to be less pressure. Okay. One other thing that you guys will definitely need to know for section 13.1 is what a barometer is. So I'll do a rough sketch of a barometer. Now, barometers will measure atmospheric pressure. So there's a way for us to measure the pressure kind of around us, the pressure of the gas that's naturally around us, and that's what we call atmospheric pressure. Now, depending on the altitude, so whether you're like on the top of a mountain or if you're at sea level, your atmospheric pressure will change. So our atmospheric pressure in Maryland is very different than the atmospheric pressure in, say, Colorado. But we're just measuring the pressure of the molecules around us. So a barometer is something that you can use. A barometer measures air pressure or atmospheric pressure. And the way that it does that is, let me actually see if I can bring this picture up to the camera. So you see this picture here. So one of the things that you notice in this picture, and this picture is also in page 386 at the bottom, let me get it straight, is this is a, there we go. This is a barometer, and so one thing that you'll notice is it has like an open beaker, and then it has a thermometer kind of looking thing sticking upside down in the beaker, and then we see a bunch of arrows pushing down. And in the beaker is actually mercury. So I'll try to redraw this on the board, but again, this is on page 386 at the bottom. So one of the ways that a barometer works is we have this beaker, and the beaker has mercury in it. So I'll just say this is mercury. And mercury is one of those weird type of elements where it's like a liquid, but kind of like a solid. And then we have this upside down thermometer looking thing that actually has little tick marks where we could actually do measurements. So the way that a barometer would work is depending on the pressure in the atmosphere, they will be pushing down on the mercury. So I'm going to draw some arrows similar to what they have in the book on page 386. Depending on the atmospheric pressure, it'll push down on the mercury and cause the mercury to go up the tube. And so you'll end up with mercury up the tube. And we could always measure and read how high that mercury goes. So the unit that they use for a barometer is millimeters of mercury, or Hg. They may abbreviate it mmHg, but that's millimeters of mercury, because actually what they do is, depending on how hard the gas around in the atmosphere, because this is an open beaker, so depending on how hard the gas molecules are pushing down on the mercury will dictate how far up the mercury goes in the barometer. So the higher the mercury goes, that means that these guys were pushing a lot more. That means that the atmospheric pressure is a lot higher. Whereas if we were to put a barometer like this on in Colorado, higher altitudes have less pressure, or less atmospheric pressure, so these arrows would not be pushing down as much, so the tube wouldn't fill up as much as it would if it were at sea level. So as an example, let's say in Maryland, we're able to get 780 millimeters of mercury, because there's a lot more air pressure here. Then if we were to go, let's say, to Colorado, we may only be able to get the mercury to fill up to, let's say here, maybe 540. So one thing to keep in mind, higher altitudes, less atmospheric pressure, lower millimeter of mercury readings, but higher air pressure, more so like at sea level, you'll be able to have larger millimeter of mercury readings. But that's just kind of in a nutshell how a barometer works. Okay. Now if we were to look at the units, because one unit that we talked about with pressure is millimeters of mercury, there's a bunch of different other units that you'll need to know for this section, and you'll need to be comfortable with converting between pressure units. There's a bunch of different ways that we can measure pressure. So the main ones that you'll need to know, and more than likely you will not be given these numbers on the quiz or even on a test, so it's important to try to memorize them as soon as you can, is, I'm going to write a bunch of units. We have 1 atmosphere, or ATM, but that just stands for atmosphere, is equal to 760 millimeters of mercury, okay, which is also equal to 101.3 kilopascals. But they will use the word kPa. This is kilopascals. Okay? And then ATM over here is atmospheres. That's what the ATM stands for. But these are some general conversions that you'll definitely be able to have to know. 1 atmosphere is 760 millimeters of mercury, which is also equal to 101.3 kPa. So the way that this would work in a potential question could be convert, let's say, 248 millimeters of mercury to atmospheres, or ATM. So if we're converting 248 millimeters of mercury to atmospheres, we'll start with what we're given. So 248. Okay. They call this dimensional analysis, but this is very similar to when you guys learned about moles and grams and those types of conversions. We'll start with what we're given. If this is millimeters of mercury here on the top, we'll want to put millimeters of mercury down here so those would cancel out. And we want to get into atmospheres, so we'll put ATMs on the top here. Now to fill in these numbers are going to come from our conversions up here, or our equivalent statements. So we know that 760 millimeters of mercury, so we'll do 760 here, is equal to 1 atmosphere. So 1 ATM there. And then all we'd have to do is just do 248, technically times 1, and then divide by 760 to get the number of atmospheres. Let's say instead we wanted to go from millimeters of mercury to kilopascals or kPa. And I'll just change this so we can kind of see a different example. Let's change this number to 347. Okay? So you want to go from millimeters of mercury, 347, to figure out what that is equivalent to in kPa. So because we're going to a different unit now, this won't apply, but we're starting with 347 millimeters of mercury. We want millimeters of mercury to be down here so that that unit will cancel with this one. And we want to go into kPa, so we'll do K or kilopascals, kPa on the top. According to our equivalent statements, 760 millimeters of mercury is equal to 101.3 kPa. So we'll do 760 here, 101.3 here. And so to actually do this math, you'd have to do 347 times 101.3, then get your answer, and then divide that by 760. So this is another thing you should be comfortable with doing, is converting from pressure units. You'd have to definitely know how to convert between all three of these, but all three of these are equal. So 1 atmosphere is equal to 760 millimeters of mercury. 1 atmosphere is also equal to 101.3 kPa. You can even look at it with these guys. So 101.3 kPa is equal to 760 millimeters of mercury. So all of these units are equal to each other. So those are the numbers you'd need to be able to do conversions. The last thing that you have in 13.1 just deals with kinetic energy and temperature. And we've talked a little bit about energy with gases and temperature with gases. So kinetic energy is by definition the energy of motion. And so we know that gas particles are always moving. So in comparison to liquids and solids, gases have a very high kinetic energy because they're always moving. Solids would have almost close to zero kinetic energy because solid particles are not moving, they're stuck together. And then liquids would have somewhere kind of in between gases and solids. They're moving, but not as much as a gas. So just remember that gases have a high kinetic energy. And we said kinetic energy, by definition, is the energy of motion. And it makes sense that gases would have the highest because they're always moving. Remember we said in the kinetic molecular theory that gas particles move in a rapid, constant, random motion. So they're always moving, so they always have a relatively high kinetic energy. One thing that we can do to give gas particles even more energy is we can increase the temperature. So if we increase the temperature, then that actually will result in an increase in kinetic energy. Okay? And the reason why that is if we were to increase the temperature of a gas, so let's say we have gas in a balloon and we heat the balloon up, almost like a hot air balloon. We're giving energy to those gas particles. They're going to move even faster than they were already moving before, so they're going to have even more kinetic energy. So higher temperature, higher kinetic energy, we can say that they are directly related. So if we were to increase temperature, then kinetic energy increases. If we decrease temperature, kinetic energy decreases. They slow down. They're not getting as much energy. Okay? And we can also tie that to pressure. So the more energy a gas particle has, the faster and more chaotic it's going to move and hit into other things, the more pressure it's going to create. But for right now, for 13.1, you definitely need to know that temperature and kinetic energy are directly related. Increased temperature, increased kinetic energy, and vice versa. All right, so we'll switch to 14.1, which is the other part of what is on your quiz. And this is relatively the same type of information that 13.1 had. The only difference is now this is getting into a little more specifics about properties of gases. So just to quickly review, in 13.1, we said gases were hard spheres that had insignificant volume. We also said that they moved in constant, rapid, random motion. And we said that gas particles have elastic collisions. So when they hit things or hit other gas particles, they bounce right back off. Now we're going to talk a little more about some of the other properties of gases. So one property that you'll definitely need to know is that gases are compressible. So these are gas properties. So one, gases are compressible. And what that means is we can squeeze them into small spaces. Because gases have very insignificant volume, they're really good with being able to be squished and things, if you think about it. So in the book, they give you the example of a airbag. So when an airbag inflates, it does have pressure, but it is able to be a little more flexible and kind of squish. If you think of a balloon too, we can usually squish a balloon, maybe not completely squeeze it, but we definitely can squeeze it more than we could, let's say, a block of wood. So gases can be compressible because we can push them really close to each other and actually put them in very compact spaces. The other thing is they want you to know some of the things that affect gas pressure. So actually, let me throw in a couple other gas properties. We know that gases have indefinite volume. And what that means is we always assume that a gas takes on the volume of its container. We can't just grab a handful of gas and measure it from our hand like we could with, let's say, a couple rocks. So gases, we always assume, have indefinite volume. They take on the volume of whatever container we put them in. So if we put them in a 2-liter bottle, we assume that they're taking up the full 2 liters. The other thing with gases is gases have an indefinite shape. Indefinite just means we can't really define it. So gases don't really have, collectively, if we take a bunch of gases together, they're not going to always form a square or a rectangle or a circle. So they take on the shape of their container. So if you see this soda can here, I will assume that gases are taking up the full 12 ounces for the volume, and I'll assume that they're taking on the shape of a cylinder, because that's the shape of this soda can. But if I were to have, let's say, this spray bottle, I'm assuming that the gases in the spray bottle take on the shape of the spray bottle. Okay? Now, if we go to some of the things that can affect gas pressure. So remember, pressure is all about force applied over an area. So the more collisions, the more pressure a gas can create. So the amount of gas can affect the gas pressure. So these are factors that change gas pressure. So factors that change gas pressure. There are 3 main ones they want you to know. One thing that can definitely change gas pressure, and if you want to think about gas pressure in terms of collisions, that probably is a good way to think about it. So the amount of a gas. So the more gas that we have, the more collisions it could create, and the more pressure it could make. Because the more collisions, the more pressure. So imagine if you have a bunch of people in a small room, you're going to bounce into each other a lot more, or get in each other's way a lot more than if you have the same amount of people in a very large room. So the same idea with gases. You put more gases into a space, they're going to hit each other more often, they're going to create more pressure. The second factor that can affect gas pressure is the volume. So that would be the size of the space or the container that you have them in. So again, if we have, let's say, 5 people in a closet, they're going to interact with each other very differently than if it's 5 people in, let's say, a gym or a large room. So if we were to change the size of the container or the volume that the gases are in, that could affect the pressure. So if we decrease the volume, making it into a smaller space, it's going to increase the pressure. You're going to bounce into each other a lot more than if we were to increase the volume. That's actually going to decrease the pressure because we have more space to spread out. We're less likely to hit each other. The third factor that can affect pressure is temperature, and we kind of talked about that a little bit. So we said that temperature and kinetic energy are directly related. So the higher the temperature, the more energy those gas particles can have. Well, the more energy gas particles can have, the more likely they're going to hit each other, and they're just going to be bouncing a lot more than if they had less energy. So if we increase the temperature, we're kind of giving the go-ahead for those gases to really bounce everywhere and create more pressure. If we decrease the temperature, those gas particles are not moving as quickly because they have less kinetic energy. They're not hitting each other more often. And if they're not hitting each other or having collisions, the pressure would go down. So these 3 factors are important. We can always adjust them either up or down to affect gas pressure. But for all of these, there are ways for us to increase gas pressure. So we'll run through it one more time. If we were to increase the amount of gas, that increases gas pressure because there's more particles hitting each other. If we decrease the volume, that increases gas pressure because if you're in a smaller space or a smaller volume, you're more than likely to hit other things more often, creating more pressure. And if we were to increase the temperature, that would also increase gas pressure. So the ways that we would increase gas pressure, we want to increase the amount of gases, decrease the volume, and we could increase the temperature. And so I'll do a little preview of, so that's all of 14.1, which will be covered on the quiz. I'll do a little preview of 14.2, which you guys may start to learn in the next few days. And this is where the calculations will come into play. So I'll just introduce the equations really briefly. And then I'll more than likely create another video on just those gas laws before you guys have your next quiz. So one thing to note, when we do these gas laws that I'll introduce in a second, the units that we use for them are very important. There are units that we have to use for these gas law equations to make sure we get the correct answers. So it's going to be very important that you're comfortable with converting from milliliters to liters, from Celsius to Kelvin. And it's also going to be important for you to be able to be comfortable with converting from different pressures like we talked about a few minutes ago. So for the gas laws, there are three that you guys will start with. The first one is Boyle's law. Okay. So Boyle's law deals with pressures and volumes. So I'll write the equation here. Okay. So it's P1V1 equals P2V2. Now what these numbers mean, P1 and V1, these are your initial volumes and initial pressures. P2V2, these are your final volumes or final pressures. If we look at these as four different variables, so 1, 2, 3, 4, in a problem, and these would be word problems that you would be given, you'll get 3 out of the 4 variables. So you may be given the initial pressure and volume, and maybe the final volume, and you may be asked to find the final pressure. So you'll be given 3 kind of numbers to plug in. You'll only be solving for the last one. But it's very important for volumes to have these in liters. So if you're given anything in milliliters, convert it into liters first. Your pressure, it's up to you what you want to use, as long as you're consistent. So if you want to use atmospheres for your pressures, that's fine. Just make sure both of these, when you put them in, already have the atmosphere for the unit. If they don't, you may need to convert. Now what Boyle says is, if we were to decrease the volume, the pressure should increase. Okay, so if you imagine pushing down on a balloon, the more I push down on the balloon, I'm squeezing it into a smaller space, the pressure in the balloon actually increases. And vice versa is true. If we were to increase the volume, the pressure should decrease. So if I now were to lift my hand up off of the balloon, I'm allowing it to go back to a larger volume, the pressure in the balloon would actually decrease. So one important thing to keep in mind with Boyle's law is that pressure and volume are inversely related. Meaning, if we were to increase one, the other one decreases. So if we increase volume, the pressure decreases. If we increase pressure, the volume decreases. So vice versa, they go in opposite directions. So pressure and volume are inversely related. Okay, this is very different than what we'll see for some of the other gas laws. Okay, the second one we'll talk about, let me scoot this down a little bit, is Charles's law. And Charles's law deals with volumes and temperatures. So he says V1 over T1 equals V2 over T2. And again, the V1s just signify your initial volumes and initial temperatures. V2s are just your final volumes and final temperatures. For these, it's very important. Your temperature has to be in Kelvin. If it's given to you in Celsius, you have to convert it into Kelvin. Volume has to be in liters. Okay? And so you can either memorize the equation like this, where all your 1s are on one side and all your 2s are on the other side. If fractions are frightening, we can actually do one where it's just multiplication. So you can actually, for the same equation, it could actually be V1 T2 equals V2 T1. Just be very careful with using this one because it switches. These are not all your 1s on one side and all your 2s on one side. It's V1 T2, V2 T1. So sometimes it's actually a little bit easier to memorize the fraction one because all your V's and T's, your initials are on one side and your finals are on the other side. But either way, both of those equations are equivalent. What Charles says is that if you were to increase your volume, so Charles says if you increase, let's start with temperature. If you increase temperature, your volume will actually increase. And so if you imagine putting a marshmallow in the microwave, it actually will expand. So the temperature will increase in the microwave, and because the marshmallow can expand, it will actually expand. Okay? The same thing is true like if we bake things. We see that as the temperature increases when we're baking a cake, the volume of the cake actually rises, and the cake increases. And so the same is true if we were to decrease temperature. So if we decrease temperature, the volume should decrease. And this is something that is true if we were to put a balloon in the freezer. It actually will seem to deflate because those gas particles aren't moving as quickly, so they're not able to hit on the inside of the container to keep the balloon inflated, and so the volume will actually decrease. So one thing to remember is that temperature and volume are directly related. Okay. So we said that pressure and volume were inversely related. Well, temperature and volume are directly related. And then I'm going to erase, well, actually we'll shift over. We're going to do the last gas law, and that one deals with pressures and temperatures. So that one is Gay-Lussac's. Okay. So Gay-Lussac's is P1 over T1 equals P2 over T2. Okay? And again, if it's easier to memorize it not as a fraction, then you can memorize it in the form of P1 T2 equals P2 T1. But just be careful because the initial and final switch. So P1 T2, P2 T1. And so what Gay-Lussac says is that if you increase the temperature, the pressure also increases. Okay? So we kind of talked about that when we were doing the atoms for the quiz. The higher the temperature, the more energy those gas particles get, the more they bounce off of each other, the more collisions they have, the more pressure or more force they're applying. Same is true if we were to decrease the temperature, the pressure would decrease. So if we could lower the temperature, the gas particles aren't moving as quickly, they're not hitting each other as often, and the pressure would actually decrease. Okay? And so we see that pressure and temperature are directly related. Just like volume and temperature are directly related, pressure and temperature are directly related. Okay? The only inverse relationship that we've talked about is with Boyle's law, where pressure and volume are inversely. If you increase one, the other one decreases. Volume and temperature and pressure and temperature are both direct relationships. And so I'll make another video before your next quiz where we'll actually go through a bunch of different examples of how we actually apply each of these equations.